Alright, welcome back ladies and gentlemen to another episode of Late Night Engineering. I'm your host, and today is going to be part one of a multi-part series that we're going to be talking about control systems and control system design. So in this video, we're going to be asking the question, what is a control system? Now, as you can see on the screen here, a control system is just an augmentation to a physical system, also known as a plant in control system design, that optimizes the transition of or maintenance of a desired output of that plant while under a certain set of inputs. So what does that mean? So what that means is when I tell the system to do something, I want the system to do that thing and to continue doing that thing for as long as I tell it to. So when I tell it to do something, that means I'm putting an input into the system, and when I want it to do something, that means I want the system to generate an output. So for example here, let's say we've just got a DC motor, no load on it, connected to a battery where we control the voltage, and I want it to spin it up to 1,200 RPM. So our input is going to be the voltage right here. That's going to be our input. The output is going to be the speed of the motor, and what we define as the system or the plant would be the motor and the voltage source together. So in this case, what we're going to do is we're just going to increase the voltage supplied until we meet our RPM. Now, in this case, if we're putting in the input and we're receiving feedback from the output, we are the control system in this example. We are maintaining and controlling the state of our system in order to get our desired output. So, if we're controlling the system, is us taking control of the leads and changing the voltage really the best way to do this? Is it the most optimal way to control the RPM of this motor? Well, to answer that question, we have to take a look at the motor dynamics. From what we know about DC motors, every motor has a certain kV constant, which, when multiplied by the supplied voltage, is equal to the free speed or no load angular rate. Alright, and this is as t goes to infinity. So this is as if you set a voltage and you let it go on for an infinite amount of time, it will approach that no load speed. So if I really wanted to get the RPM that I wanted out of this motor, why couldn't I just set it to the voltage that's defined by this equation? So I just set the no load omega to our 1,200 RPM, and then just solve for V supplied and set it at that voltage. Is that really the best way to do it? Yeah, I mean, you could get to that velocity angular rate. You would get there eventually, but is it really the fastest way to do it? That's what we want to ask, because when you apply that voltage, so we have time in the x-axis, and we have omega in the y-axis, and then we say 1,200 RPM. So when we apply, and we'll just have it a separate graph here for voltage, or time and then voltage. So if we know our V motor, I'm just going to say V motor, the voltage that we would need to supply to the motor to get 1,200 RPM, if we just set it at that value, what's going to happen is the motor is going to speed up. Over time, it's going to get to what we want. But if we know that voltage, or that omega is proportional to voltage, the voltage supplied, then what we can do is we can input more voltage than what we really need to get to our RPM, and then over time decrease that voltage in order to get as fast as possible to our desired RPM, right? So if we said instead, well, hey, let's just have a really high voltage, that'll get it spinning really quickly, and then just tapered it off over time, we could get a much better response out of the system. We could get to our desired, ideally what we want is we just want it to go as quickly as possible to our desired state and just stay there, right? We don't have to wait all that time for it to spin up. So when we're controlling the speed of this motor, we're probably going to do something where we have it at really high RPM and then we lower it and we adjust it back and forth as we kind of dial in on that exact voltage to get what we want out of the system to get our speed. So it'll look something like this. So we kind of go back and forth as we try and dial in the speed. We make finer and finer adjustments to the voltage. But what we really want to know is, what is this function voltage over time that optimizes our transition from a zero initial condition to our 1200 RPM? That's what we want to know. So in order to find our optimal V of t, what we need to do is we need to first characterize our motor plant system. So to do that, the way we're going to set this up is just a really simple electrical circuit. We are supplying a voltage V source here. It's going through, we can model a motor as basically just a resistor and an inductor with a certain back EMF represented by VB of t here. So we are supplying voltage as a function of time, current as a function of time is changing, the impedance due to the resistor and the inductance of the inductor within the motor are staying constant, and the fixed magnetic field is ostensibly what the permanent magnets are within a stator of the motor itself. So if we do just a really simple current loop over here, we end up with this equation right here. So we end up with that equation right there. So we just have going through, we just have the voltage of the resistor is just the resistor times the current as a function of time. The voltage over the inductor is the change in current over change in time times its inductance. And the back EMF of the stator within the motor itself is the voltage constant times whatever speed it's going, which is equivalent to the source voltage that we're applying over here, which is what our input into the system is. So what we also know about motors is that the torque, so we've got current, right now we've got current here with omega here as a function of one of our inputs. Now omega is our output, it's our angular rate of the motor versus time. We want to try and find a way to get rid of current as a function of time. But fortunately we know that the torque of the motor is equal to a constant times the current as a function of time. So we can just kind of rearrange this and say that current over time is equal to a function of torque divided by some constant. Now if we sub all of this back into the original equation, what we get is this bad boy right here. So we do, and just a little bit of rearranging here, what we can get, completely forgot. So with a little bit of rearranging, we can also assume that the torque of the motor as a function of time acts as kind of like a viscous damper to the system. So we can say that the torque over time is equal to d times some constant d times omega t. So we then plug all of that back into our original equation, do some rearranging, and we end up with this equation right here. So this LA, this DM, KT, RA, KV, those are all just constants, and we do what all good engineers do, is we just kind of represent them as just big constant blocks. Now I know these two constants are different, but for the sake of this, we're just going to look at the overall structure of this equation. So let's take a look here. So we've got Vs of t as our input into the system, and we have two terms which are directly related to omega t and a bunch of constants right here and right here, represented in the equation on the left. So this is basically just a first order linear ordinary differential equation that we can solve for. That we can relate to whatever function we're putting in for v of t to get an output of omega t. So ostensibly what we're doing is shown right down here, is we get Vs in to our plant and getting out omega t. Alright, just to recap, in this video we've gone over what a control system is. It's basically just an augmentation to an existing physical system or a plant that changes or optimizes its behavior to fit our desired characteristics. We then went over an example where we were controlling a DC motor with an input of voltage and an output of RPM. What we then did was we fully defined the relationship between our input, our voltage, and our output, our RPM. In next week's video, we're going to start going over the Laplace transform, as well as we're going to start going over transfer functions, which will help us when designing our control systems. Alright, until that point, see you all, have a good night, I'm signing off.